Okay. So, just quick quiz, I think people did okay on it, it looked like. I wasn't seeing all the steps on many papers. So it kind of looked like you're using Gauss's law. But turns out that most or all of you weren't. And there's one where it was actually written out very clearly what the steps were. And I saw it as afraid of seeing. And didn't get it right anyhow. Okay, well. We use E for the electric field, we use A for the area. Okay, E is KQ over R squared. In the area is 4 pi R squared. Here's an important step. I didn't expect anybody to write it out, and I was satisfied with this much. Okay, the field is radial. It's always perpendicular to the surface. Always long, okay? So when I say the flux is field times area, it's the component of the field perpendicular to the normal. Okay. So I could write E perpendicular here. E is this. Field is always radial, always perpendicular to the surface. So the component of E perpendicular to the surface is E. Okay. Okay. I usually don't use epsilon naught, but when we talk about capacitors and stuff like that, it's very handy. Okay. So I usually talk about K simply because K is easy to remember. What's 1 over 4 pi? And because epsilon naught, if K is 1 over 4 pi epsilon naught, if you solve that for epsilon naught, you get epsilon naught is 1 over 4 pi K. What's 1 over 4 pi times 9 times 10 to the 9th? Newton meter squared per Coulomb squared. It's in units Coulomb squared per Newton meter squared. Okay, what's the number? It's not easy to remember. Okay, I always prefer to use K on the call. And it almost always can. Okay, so that's just one. Want to make a little note in epsilon naught. Wanted to review just the basic idea. And then what did we say last time? Through arguments that we can make from multivariable calculus. Your book actually has kind of a neat argument. You know, put the charge at the center of a sphere, and then take a little area in the sphere and project it out to whatever irregular shape might be surrounding that sphere. And then use cosines and stuff like that. Like it's a pretty neat argument. Essentially, you know, it's a multivariable calculus argument. But we're going to prove it a little different way. Okay. When we do multivariable calculus. In any case, Now, the upshot is for any combination of charges or any distribution of charges, the flux through any surface that encloses that charge is equal to 4 pi k cubed. Okay, or cubed epsilon naught. So what I want to do now is let's assume that you have a uniform charge density rho in units of charge per unit volume, right? What's a field in a sphere of radius A? And you're going to want to use Gauss's law for that. Okay, we're having more trouble than I would have expected. I've expected a little bit of trouble here. Let's look at the whole situation. Okay. What's Gauss's law tell you? It relates specific and that as clearly as possible to avoid confusion. It relates to closed charge and a flux, right? And what's flux? It's perpendicular component of the field times the area. Okay. So what can you determine from the given information? Well, density is charge per unit volume in the field. I'm sorry, and you have a sphere of radius A. Implicitly, that sphere encloses some of this charge, right? This charge of density rho is implicitly inside the sphere, very likely outside the sphere too, because you do bigger or smaller spheres. So we're in a region where the density is this, and now we're asking for the field on a sphere of radius A. So what can you determine? Well, with the recorder on, so I'm not going to ask for an answer, but you're going to determine the amount of charge. Now, if you know the amount of charge, well, you've got a very simple relationship between two quantities, charge and flux. You know one, you know the other. So once you know the charge inside the sphere, you can find the flux. And then what's a flux related? It relates field and area. So flux, field, and area are related. If you know two of these things, you can find the third. Okay. So Gauss's law relates to charge and flux, so you know the flux. Okay. Trying to find the fields, you better know the area. That makes sense? Think it through until it really does. Because that's a centered That's a central intuition you need to apply Gauss's law. Once you get that concept firmly in your mind, things get reasonably easy. I say reasonably because certain situations can be challenging. Okay, well. Enclosed charge is rho times volume which is rho times 4 pi a squared, right? We have 4/3 pi a cubed. Okay, so flux is 4 pi k times 4/3 pi a cubed, isn't it? Okay, because I don't have my rho in there. Which is unfortunate that there have room to write it. Right, here we go. Okay. Flux is four pi k times 4/3 rho, 4/3 pi rho a cubed, right? Okay. And the area is 4 pi r squared. Okay. So now, once more, either confirm or it's 4 pi a squared. So what's the field? Write it out. Compare it with what you have. Okay, so okay, this could be simplified. I got 16 pi squared k rho a cubed over 3. But I want to leave it this way in factor form because it's going to be more straightforward to divide by the area, which is what we're ultimately going to do. So what? This could all be written out in terms of symbols, but you're not relating to the symbols that naturally after only a couple of days. Okay, and not having an entire assignment to do 5 days hence. So the field perpendicular is flux over area. Field is perpendicular. To the surface. By symmetry. Important step. of the field, not just the perpendicular component of the field, the entire glorious field is. Well, whatever. Right on that line, there's 4 pi k. Well, divided by the area. This 4 pi will divide that 4 pi. A squared will divide a cubed, so we'll get an A, and then everything else. It's gonna be gonna have 4/3 pi k rho. Let's divide out. Now, the implication of this is you have a constant multiple of A. So if you do a larger and larger sphere, you get a bigger and bigger electric field. Okay. So a cloud is a thunderstorm. Now you don't have a uniform charge density, but you have some kind of a over at least regions of the cloud. And I'm not a meteorologist, so I'm lying. I'm not lying, but if I'm perpetrating something that isn't true, don't quote me. Okay. But if we assume, let's just assume that you have over some region, 100 meters square, size of football field, a sphere maybe, okay? In closing, some more or less uniform charge, you're going to get a really big field compared to what you would have if you had only a 10-meter sphere. And you'd have 10 times the field. And if you accumulate charge in a bigger and bigger area, you get a bigger and bigger field. When the field gets big enough, you get lightning. Okay. So there's some relevance to this model. That's not exactly what goes on in a cloud, but you get the idea. If you have enough charge distributed over big enough, if you have some, you know, even a small charge density over a big enough region, the charge density doesn't vary a whole lot. That's how you get light. All right. So that's kind of important. That's an important model. It conceptually gives you a good picture of Gauss's law and something besides the simple examples we did on Monday. Now, those examples are central also, but this extends it a little further. Okay, let's say we have a spherical charge distribution about the origin. By that, I mean, you got an origin here, okay? We don't need X, Y, and Z coordinates because everything's spherically symmetric. So at any distance R from the origin, the field strength is, at any distance R from the origin, the density is some constant divided by R. So C is going to be a constant. You have to give it any more than that. It could be any constant. So field is inversely proportional to your distance from the origin. Sorry, the density is inversely proportional to the distance from the origin. And now we want to find a field at a distance A from the origin. Okay. So we create a Gaussian surface. Now the shape of the Gaussian surface depends on the situation. In this case, Gaussian surface is going to be a sphere, and that's fairly obvious. And since you're trying to find the field at distance A, you're probably going to use a sphere of radius A. You can do something very similar to what you did here. Okay. So you're going to run into a snag, but let's see what it is. How are you going to approach this? Give you just a couple of minutes. Again, very similar, but with a big difference because of the non-constant nature of rho. Okay, just move things along a little further. The Gaussian surface. Sphere of radius A, and then think back to what we did here. Okay. The logic is identical. The only difference between what we did here and what you do here is a little trickier to find the amount of charge within that sphere. But the logic of the solution is identical. Flux, well, Gauss's law relates charge and flux. If you find the charge, you find the flux. And then flux is field times area. It's a perpendicular field, but you have certain symmetry. So everything's nice and perpendicular. So flux is just going to be the field times the area. And you know what the area of the sphere is. So the central thing is find the charge inside that sphere. How are we going to do that? Any suggestions? Let's talk about it. Because I probably going to have to help you along a little bit on this. Okay, so we see, just as in the previous example, the flux is just a multiple of the charge. So if we know the charge, we know the flux. And in this situation, everything's nice and symmetric. We have a sphere, spherical Gaussian surface. Area is 4πa squared. Okay. Everything follows just as easily as it did in the previous example. Once we know the charge. Get the charge. You don't have a constant charge density. We can't just multiply the charge density by the volume. Don't work. Well, here's how we're going to set it up. We've got a short time and I have to do this kind of quickly. We partition the interval 0a. So we partition the interval from 0 to a. And we just ask ourselves, what happens in a typical interval? So a typical interval. Okay, let's just say we're down in the XY plane. We've got R sub I here. And do that R sub I minus 1. And this is R sub I. Okay, in the plane, there's going to be a ring between R sub I minus 1 and R sub I. And you know, if delta R sub I is difference R sub I minus 1, then delta R sub I times 2 pi R star. Okay. We rotate that ring. Okay, and we get a shell of a sphere. Okay. Thickness of the shell is delta R sub I, which is Ri minus 1. And the radius is approximately Ri star, your sample point within that interval that I haven't documented here, but that's implicit. There's a sample point, and we always have a sample point, and we do things in terms of what happens in the sample. So the volume is 4 pi Ri star times delta Ri. 4 pi Ri star is the surface area of that sphere. Okay, get the sample point. We multiply it by the thickness and we get the volume of that shell. Charge. Charge density C over R. Where are we going to sample the density? At the sample point. It's C over R sum by star. So sum of the delta Q supply is sum of this volume times density. Factor out the 4 pi C. And it's 4 pi C times Ri star over R sub I. We have Ri star here and R star squared there. And it's approaching the integral from 0 to A. Written that. Okay. Now C is going to have units such that when you divide C by R, you get mass per unit area or over volume. So as far as your length increments, C is going to have units of reciprocal R squared. Right. Now it's got to be reciprocal R to the fourth. Okay. So how the units are working out here. Anyhow, if I've done these details right, which I think I have. Get 4 pi C times A squared over 2. In the units of C, we're going to end up giving you units of charge. Okay. What I said initially, C would be in units of charge per unit per square unit of coulombs per square meter, charge per square length units. Okay, so that's like coulombs per meter per square meter. That's in square meters. It's disturbing me. It's going to be something like that. Okay, do it carefully. And it should work out. I don't like the way they use it. I don't want to take the time to write it out. 3 minutes overtime, that's as far as I want to take it. Okay, so you got to do this integral. And this is a fairly simple integral if you understand spherical shells. And calculus is a good shell method of integration, mostly with cylinders. But you might want to review that because you are going to need to be able to set up and do this integration. Okay. Okay, I was right with everything I said when we said that's gotta be coulombs per square meter, which is pretty obvious. That's in coulombs per square meter, then like you divide by meters, you get coulombs cubic meter, which is units of charge. Units of charge density. Charge per unit volume. It's not meters, it's some other length unit. It's in units of charge for season units of charge per length units squared. Ours in length units, you get charge per length unit cube, which is unit of charge per volume. Using coulombs and meters as I use. We see then that C here is in units of coulombs per meter squared, as I said. And of course, A squared is going to be units of meter squares. At coulomb per meter squared times meter squared, which is coulombs. Could imagine what was wrong. I don't know how I was looking at that and not seeing it because I had all the parts, but that's what it is. Okay, so there we have it. I believe this interval is correct, but check it over yourself. I did it kind of quickly. It's not totally possible that I could be wrong. Once you have this, of course, then you simply divide this by the area and you get the electric field. So, complete the exercise. What's the surface area of your Gaussian surface? It's 1 pi a squared. So you get a very simple result for the electric field, and you find how it changes with distance from the origin.